Welcome to this problem walkthrough. Today, we'll be diving into the problem titled Maximum Number of Words You Can Type. In this session, we'll explore the problem statement, break it down step by step, and analyze different approaches to solve it. Let's get started. In this problem, we are tasked with determining how many words from a given text can be fully typed on a keyboard, considering that certain keys are broken. The text consists of words separated by single spaces, and each word is made up of lowercase English letters. Additionally, we are provided with a string of broken letters, which represents the keys on the keyboard that are not functioning. A word can only be fully typed if it does not include any of the broken letters. The goal is to return the maximum number of words from the text that can be typed given these restrictions. For the input, we have two components, the text, which is a string of words, and broken letters, which is a string of unique lowercase letters representing the broken keys. The output will be a single integer indicating the maximum number of words that can be typed. Let's look at some examples to clarify how this works. In the first example, the input text is "Hello World," and the broken letters are at ND. The words in the text are "Hello" and "World." Hello can be typed because it does not contain any of the broken letters A or D. However, world cannot be typed because it contains the broken letter D. Since only one word, hello, can be fully typed, the output is 1. Now, in the second example, the text is LeetCode, and the broken letters are L and T. The words are Leet and Code. This time, neither of the words can be fully typed. Leet contains both L and T, while Code contains T. As a result, the output is 0, indicating that no words can be typed in this case. In the third example, the text remains LeetCode, but this time, there are no broken letters. This means that all keys on the keyboard are functioning properly. The words are Leet and Code. Since there are no broken letters, both Leet and Code can be fully typed without any issue. Therefore, the maximum number of words that can be typed in this situation is 2. This example highlights the case where the absence of broken letters allows every word in the text to be typed. To summarize this example, both Leet and Code are fully typable when there are no broken letters, so the output is 2. Now, let's consider the constraints and edge cases. The length of the text can go up to 10,000 characters, and each word in the text consists only of lowercase English letters. The broken letters string can be empty, meaning no keys are broken, or contain up to 26 unique lowercase letters, which would represent all keys being broken. Edge cases include scenarios like no broken letters, where all words can be typed, or all letters being broken, where no words can be typed. In cases where the text is a single word, the result depends on whether that word contains any broken letters. Finally, for large inputs, such as when the text is close to 10,000 characters or all 26 letters are broken, the solution must remain efficient and handle these situations seamlessly. To solve this problem, one intuitive method is the brute force approach. The idea here is straightforward. We iterate through the text, split it into individual words, and then check each word to see if it contains any of the broken letters. If a word doesn't contain any broken letters, we consider it typable. To implement this, the process begins by splitting the text into words using the split function. Then, for each word, we check every character in that word to see if it matches any of the characters in the broken letters string. If a word passes this test, we increment our count of typable words. While this method is quite simple to implement, it does have limitations in terms of efficiency. Specifically, the nested loop structure, where we check every character of each word against the broken letters, can become a bottleneck for larger inputs. The time complexity here involves splitting the text, which takes n, and then performing character checks, which depend on the average word length and the number of broken letters, leading to an overall complexity of n plus m*k. This makes the brute force approach less practical for scenarios with large input sizes. A more efficient solution can be achieved using an optimized approach that leverages the power of sets. This is because checking membership in a set is much faster, with an average time complexity of 1. To begin, we convert the broken letters string into a set, which allows us to perform constant time lookups. Next, we split the text into individual words as before. For each word, instead of checking every character individually, we determine if there's any overlap between the word's characters and the set of broken letters. If there's no intersection, the word is considered typable. This is a significant improvement because we avoid repeatedly scanning through the broken letters string. In terms of time complexity, creating the set of broken letters takes O(k), splitting the text into words takes O(n), and checking each word where we compare its average length m against the set takes O(m), resulting in an overall complexity of O(n plus m asterisk w), where w is the number of words. This approach is not only faster but also scales well for larger inputs, making it a strong candidate for solving this problem efficiently. In Python, we have another option to solve this problem using list comprehensions, which can make the implementation more compact. This approach still relies on the optimized use of sets but condenses the solution into a single, elegant statement. First, we convert the broken letters string into a set to enable faster lookups. Then, using a list comprehension, we filter the words by checking if all characters in a word are not part of the broken letters set. This check is performed using Python's built-in all function, which returns true only if every character in the word passes the condition. Finally, the length of the resulting list gives us the number of typable words. While this method is functionally equivalent to the set-based optimized approach in terms of time complexity, O(n plus m asterisk w), its compactness may appeal to experienced Python developers. However, it can be less intuitive for beginners due to its condensed syntax, making it slightly harder to read and understand at first glance. After evaluating the different approaches, we chose the optimized approach using sets as the ideal solution. This method strikes the perfect balance between clarity, efficiency, and scalability. The key insight here is that the repetitive character checks in the brute force method can be avoided entirely by leveraging a set, which allows for constant time lookups. This optimization leads to significant performance improvements, especially for larger input sizes. When comparing the approaches, the brute force method is simple but suffers from inefficiency due to its nested loops. On the other hand, the list comprehension approach is compact and Pythonic but may sacrifice readability for those new to the language. The set-based optimized approach, however, is both intuitive and performant. It provides clear logic while ensuring the solution remains efficient and scalable, making it the best choice for tackling this problem effectively. To solve this problem, we need to determine how many words in the given text can be typed using the functioning keys on a keyboard, given that some keys are broken. The process begins by parsing the input. First, we extract the text and the set of broken letters. The broken letters are best represented as a set because sets allow for efficient O(1) lookup times. Next, we split the input text into individual words using the split method. This method divides the string into a list of words, using spaces as delimiters. For instance, the text "Hello World" would result in the list "Hello World." Once we have the words, we can proceed to checking each word against the broken letters to determine if it is typable. After splitting the text into words, we initialize a counter called typable_count to 0. This counter will keep track of the number of words that can be typed using the functioning keys. For each word in the list, we check if any of its characters belong to the set of broken letters. This can be done efficiently using the any function combined with a generator expression, which evaluates each character in the word. For example, any char_n broken_set for char_n word will return true if any character in the word is found in the set of broken letters. If no characters in the word are broken, we increment the typable_count by 1. Finally, once all words have been processed, the value of typable_count is returned as the result. This value represents the total number of words that can be typed using the functioning keys. This algorithm is designed to be both efficient and robust. By using a set to store broken letters, we ensure that membership checks, such as determining if a character belongs to the broken set, are performed in O(1) time on average. Additionally, the use of the any function allows for early termination when checking a word. As soon as a broken character is found, the function stops further evaluation, saving unnecessary computation. Several edge cases are also accounted for. For example, if the input text is empty, the result should naturally be 0 since there are no words to evaluate. If no keys are broken, then all words in the text are typable. Conversely, if all keys are broken, no words can be typed. The presence of duplicate letters in the text or in the set of broken letters does not affect the outcome, as the set-based approach inherently handles duplicates. Now let's analyze the complexity of the key operations in this algorithm. Splitting the text into words using the split method has a time complexity of O(n), where n is the length of the text. This is because each character in the text needs to be processed to identify word boundaries. Checking each word for broken letters introduces a complexity of O(m*k), where m is the number of words and k is the average length of a word. This arises because, for each word, we iterate over its characters and perform membership checks against the broken letters set, which takes O(1) per check on average. Combining these steps, the overall time complexity of the algorithm is O(n plus m*k). The operations are sequential, so their complexities simply add together. This makes the algorithm efficient and scalable for large inputs. This Python implementation solves LeetCode problem number 1935, maximum number of words you can type. The goal is to determine how many words in a given text can be typed without using broken keyboard letters. First, the broken letters are converted into a set for efficient O(1) lookup. This ensures that we can quickly check if a letter is broken while iterating over the words. Next, the input text is split into a list of words using the split function, which separates the text by whitespace. We initialize a counter count to track the number of words that can be typed successfully. Then, we iterate through each word in the list. For each word, we use the any function to check if any of its characters are present in the set of broken letters. If no characters are broken, the word is considered typable, and we increment the count. Finally, the total count of typable words is returned as the result. This implementation is efficient with a time complexity of O(n*m), where n is the number of words in the text and m is the average length of the words. The approach ensures clarity, correctness, and optimal performance for the given problem. Here, we begin by importing the necessary packages and defining our class and method. The method, can-be-typed-words, takes two inputs, text, which is a string of words separated by spaces, and broken letters, which is a string of characters representing keys on the keyboard that are broken. The first step is to convert the string of broken letters into a set of characters. This allows us to perform fast lookups when checking if a character is broken. Next, we split the input text into an array of words using the split method, which separates the text wherever there's a space. After that, we initialize a counter, count, to keep track of how many words can be typed without using any of the broken keys. Finally, we use a for loop to iterate over each word in the text. For each word, we assume it can be typed, setting a Boolean variable canType to true. Then, we check each character in the word to see if it exists in the broken set. If we find a match, the word cannot be typed, so we set canType to false and exit the loop for that word. If, after checking all the characters in a word, the canType variable remains true, we know the word can be typed without using any broken keys. In this case, we increment the count variable. Once we've processed all the words in the input text, we return the value of count, which represents the total number of words that can be typed. This implementation efficiently checks each word against the set of broken keys, ensuring that the solution is both clear and performant. By leveraging data structures like sets for quick lookups, the approach minimizes unnecessary computations and keeps the code straightforward and easy to understand. Let's start with example 1, where the input text is Hello World and the broken letters are add. First, we convert the broken letters into a set for quick lookup, resulting in broken_set containing an ND. Next, we split the text into individual words, giving us the list, Hello World. We then initialize a counter count to 0, which will track how many words can be typed without using any broken letters. Now, we examine each word in the list. For the word hello, we check each character, H, E, L, L, and O. None of these characters are in broken_set, so we increment count by 1. Moving to the next word, world, we again check each character, W, O, R, L, and D. Here, the character D is found in broken_set, meaning this word cannot be typed. As a result, we skip it. After processing all the words, the final count is 1, which is then returned as the output for this example. For example 2, the input text is cat dog, and the broken letters are Z. We start by converting the broken letters into a set, resulting in broken_set containing just Z. Splitting the text into words gives us the list, cat, dog. We initialize count to 0, as usual. Now, for the word cat, we check each character, C, Y, and T. None of these are in broken underscore set, so we increment count to 1. Then, we check the word dog. Its characters D, O, and G are also not in broken underscore set, so we increment count again, bringing it to 2. Since all words in the text can be typed without using broken letters, the final count is 2, which is returned as the output. Now let's analyze example 3, where the input text is apple orange and the broken letters are A-E-I-O-U. First, we convert the broken letters into a set, resulting in broken underscore set containing the vowels of E, I, O, and U. Splitting the text gives us the words, apple, orange. We initialize count to 0. For the word apple, we check each character, A, P, P, L, and E. Here, both A and E are found in broken underscore set, indicating that this word contains broken letters. As a result, we skip it without incrementing count. Next, we examine the word orange. Its characters O, R, A, N, G, and E include O, A, and E, all of which are in broken underscore set. Since the word orange contains broken letters, it is also skipped. After evaluating both words in the text, no words remain that can be typed without using broken letters. Therefore, the final count is 0. This value is returned as the output for this example, demonstrating that when all words contain at least one broken letter, the result is 0 typable words. The time complexity of this solution can be analyzed step by step. First, consider the process of converting the broken letters string into a set. If M represents the length of the broken letters string, this operation takes M time because each character is added to the set exactly once. Next, we move to splitting the input text into individual words. If the string text contains n characters in total, the split method scans the entire string to identify word boundaries, which also takes n time. These are the initial steps contributing to the algorithm's time complexity. Now, let's examine the step where the algorithm iterates through each word in the text and checks for broken letters. If there are k words in the text and the average word length is w, the for loop processes all k words. For each word, the any function checks whether any character in the word exists in the broken underscore set. Since checking membership in a set has an average time complexity of 1, iterating through all w characters of a word takes w time. Therefore, the total time complexity for this step is k*w. Since the sum of the lengths of all words equals the total number of characters in text, or n, this simplifies to n. When you combine all the steps, the overall time complexity becomes m plus n, where m is the length of broken letters and n is the length of text. Now, let's explore the space complexity of the solution. First, the broken underscore set is created to store up to m unique characters from the broken letters string, requiring m space. Then, the split method generates a list of k words, where k represents the number of words in the text. In the worst case, where every character in the text is separated by spaces, the list could contain up to n words, requiring n space. Additionally, the algorithm uses a few temporary variables, such as count and word, which require 1 space. Combining these factors, the total space complexity is m plus n, where m is the length of broken letters and n is the length of text. Let's compare this efficient approach to a naive one. In a naive solution, we would iterate through each word and check every character of the word directly against the broken letters string. Without converting broken letters into a set, this would involve a time complexity of k*w*m, where k is the number of words, w is the average word length, and m is the length of broken letters. By using a set for broken letters, we reduce the lookup time from m to 1, which optimizes the overall complexity to k*w, or simply n. Furthermore, the time and space complexity remain m plus n, regardless of edge cases, as the algorithm processes all characters in the text and broken letters, ensuring consistent performance. Finally, let's solidify this with a mathematical proof of the big O complexity. The algorithm performs two primary operations, a single pass to build a set from broken letters, which takes m, and another pass through the text string to process its characters, which takes n. Since these steps are sequential and independent, the total time complexity is O, m plus n. Similarly, the space complexity is determined by the storage required for the broken underscore set and the list of words, both of which together use O, m plus n, space. By bounding both time and space complexity within these terms, we ensure the algorithm remains efficient, even for large input sizes. In this section, let's address some common mistakes that can trip you up while solving this problem. First, failing to account for edge cases, such as empty strings or scenarios where there are no broken letters, is a frequent oversight. This can lead to runtime errors or incorrect results since iterating through words in these situations might not behave as expected. The solution is to always test your code with edge cases like empty strings, no words provided, or no broken letters at all. Next, another mistake is repeatedly checking for broken letters in each word. This approach introduces redundant checks and unnecessarily increases the time complexity of your solution. Instead, you can store broken letters in a set, which allows for constant time lookups for each character. Finally, incorrect handling of case sensitivity is another pitfall. If the problem specifies case-sensitive behavior but your solution doesn't account for it, you may overlook valid or invalid words. To fix this, make sure to carefully follow the problem requirements and normalize the case if needed. Now, let's explore two more common issues and how to address them. One is not optimizing for large inputs. If you're working with a large number of words in the text, a brute force approach that repeatedly checks each character can easily lead to time limit violations. To handle this, consider optimizing your solution by pre-computing valid or invalid words and using efficient data structures, like sets, to minimize redundant operations. Another common mistake is overcomplicating the solution. Adding unnecessary data structures or extra logic might make the code harder to understand and even slower in practice. The best approach is to keep your implementation as simple as possible while meeting the problem's requirements and ensuring efficiency. Next, let's discuss some key interview insights related to this problem. Recognizing the underlying pattern is critical, as this problem often falls under the category of string parsing and filtering. Pre-processing, such as storing broken letters in a set, is an essential technique to emphasize. Additionally, interviewers often focus on optimization, so be prepared to discuss trade-offs between a brute force method with a time complexity of O, n asterisk m, and optimized approaches that can achieve O, n plus m, where n is the number of words and m is the number of broken letters. Demonstrating awareness of edge case handling is another way to stand out. For example, explaining how you'd handle scenarios with no broken letters or words that contain no characters shows thoroughness. Finally, be ready for follow-up variations of the problem. These could include allowing partial word matches, introducing additional constraints, or adapting the solution for multilingual text. Being flexible with your approach is key. Let's connect this problem to related challenges you might encounter. For instance, in LeetCode 1165, single-row keyboard, the goal is to calculate typing time on a single-row keyboard, which involves efficient string traversal and indexing, concepts that overlap with this problem. Another example is LeetCode 819, most common word, which focuses on string parsing and filtering, particularly ignoring specific banned words. Similarly, LeetCode 20, valid parentheses, requires efficient processing of strings and the use of appropriate data structures like stacks. Finally, LeetCode 648, replace words, deals with replacing strings efficiently using a tree or set, which is closely related to filtering out invalid words in our current problem. These problems share foundational techniques, so mastering them can help you build transferable skills. To wrap up, let's examine some alternative approaches and the trade-offs involved. The brute force approach is straightforward: iterate through each word and check if it contains any broken letters. While simple to implement, it's O, n asterisk m, time complexity, where n is the number of words and m is the average word length, makes it unsuitable for large inputs. A more efficient alternative is the set-based approach, where broken letters are stored in a set for O(1) lookups. This reduces the complexity to O, n plus k, where k is the total number of characters across all words. It's optimized for larger datasets but does require additional memory. For those looking to push efficiency further, the bit masking approach is a more advanced technique. By representing broken letters as a bit mask and using bitwise operations to validate words, you can achieve an O(n) complexity. However, this method can be harder to implement and debug, especially under interview conditions. Choosing the right approach depends on the problem constraints and your familiarity with these techniques. Great job! We've successfully solved the problem, analyzed its complexity, and gained key insights along the way. Make sure to practice similar problems to strengthen these skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!